Hello, this is my presentation for the DATA605 final project. The project consists of two parts, problem 1 and problem 2. Problem 1, we ask to generate 10,000 random uniform numbers and select from numbers 1 through n, where n is greater than or equal to 6, and also generate 10,000 random normal numbers with mu and sigma equals to n plus 1 over 2. So this is the section that generates these numbers, and I chose n to be 30, so that we select numbers from 1 to 30 and do 10,000 selections of those randomly. So in part 1 we essentially given three different we asked to calculate probabilities for three different conditional probabilities, and I provide the R code and the formulas to calculate those. Essentially, the trick was to, for example, to find the probability of x greater than little y. It was just a matter of selecting those x that satisfy that condition and dividing that by the total number of selections, which is 10,000. So that gives us the portion of those numbers of x that are greater than or equal to little y, which is the probability for that condition. So that's part 1. In part 2, we asked essentially if the probability of x is greater than little x and probability of y is greater than little y is the same thing as the probability of those two conditions multiplied, which essentially is asking us, can we treat the x and y independent? And to show that using the simulation, we asked to build a table and evaluate the marginal and joint probabilities. So to build the table of counts, I went with the strategy of building up a Cartesian product of the two distributions, the 10,000 uniform distributions against 10,000 normal distributions. So that gave me a way to get the exact count under each joint condition. For example, the count of 3,484 is for those values of x which are greater than little x, and at the same time for those values of y which are greater than y. So given that table count, it was pretty trivial then to find joint probabilities and marginal probabilities, and I provide the formulas for those as well. So at the end we can say that the two sides of the equation are pretty much equal. So when we multiply the probabilities of the two events independently, we get the value of 0.3487, which is what we expect if the x and y were truly independent. And we can say that they are, because our actual value is 0.3484, which is very close. So how close, and to prove that the two x and y are independent, we do that in part 3. We use the Fisher exact test and the chi-square test. And For the Fisher exact test, I'm using the hypergeometric distribution to essentially give us the probability of how close or how far we are from the expected value. So if we are too far from the expected value, then so our probability will be is small, then we can reject the hypothesis that the x and y are independent. So in this case we got a probability of 0.5474 using the p-hyper function, and which tells us that it is a large probability, and therefore we cannot reject the null hypothesis. So that therefore we should maintain the claim that x and y are independent. And we come to the similar conclusion using the chi-square test. The chi-square test involved a little bit more calculation, where basically to calculate the chi-square value we need to compare the expected value from the observed versus observed values, and using the formula given here. And then we can follow the same principle of finding the probability that tells us how far we are from the expected value. If the probability is small again, then we can reject the hypothesis that x and y are independent. However, using the chi-square test, my probability value was 0.89, which is rather large, and therefore again we maintain the claim that x and y are independent. So we come to part 2 of the part 2 of the project is basically participating in the Kaggle competition for predicting house prices. In part 1 we asked to do some descriptive and inferential statistics, and I do that here by taking a look at the gr_live area variable from the training set, and that variable stands for the ground level ground living area in square feet. So I'm just doing basic summary on the variable, and then showing a histogram for the values and superimposing a blue line of what the normal distribution might look like. And then I do the same thing, a summary and a histogram with the normal distribution comparison for the sale price variable. And finally I see if there's if there's a correlation, linear correlation between the two variables. And here I present the scatter plot with the regression line, and the residual plot followed by the QQ plot, which essentially indicates that there should be a pretty strong linear correlation between the ground living area and the sale price. So I expect the ground living area to be a good predictor for the dependent variable. So subsequently we asked to generate a scatter plot matrix and to include additional variables. So I decided, in addition to the ground living area, I would include the bedroom above ground level area, and the year built variables to be included in the scatter plot matrix. And here's the matrix showing those variables and how they relate to each other. And the non-graphical way to see correlation between the variables is to do this correlation matrix. And I'm using the core function from R, and it gives us this matrix, 4x4 matrix here, with the correlation values between each pair of variables. And then below, I'm performing the pairwise correlation testing, and we are to show that whether the test would support the hypothesis that the correlation value is 0. Sorry, one second. So here we're performing pairwise correlation test that between each pairwise set of variables is not 0. So our null hypothesis is that the correlation between the pairwise set of variables is 0. However, my testing indicated that that's not true. So using the 80% confidence interval. So I'm using the core.test R function to do the testing. So for example, I'm comparing the pairwise correlation of ground living area and the year built, and we see that even though the correlation value is small, it's still not 0. That means the alternative hypothesis is true, and that means we're going to reject that the two variables are independent. Similar results for the other pairwise comparisons. So despite the fact that the hypothesis we rejected the hypothesis based on those tests, I would be worried about the family-wise error, which is basically the type 1 error of incorrectly rejecting the null hypothesis. And the reason for that is that there are a lot of observations, and the likelihood of committing such an error is pretty much guaranteed.